Part D. Find the total distance traveled by the particle over the time interval between time t equals 0 and t equal 3, or t 0 is less than or equal to t is less than or equal to 3. So let's draw some axes here to just make sure, and you wouldn't obviously have to do this if you were doing it under time pressure during the actual AP exam, but my point here is to make sure that we all are understanding what's going on. So when t is equal to 0, where are we? Well, they tell us x of 0 is 0, so x is 0, and y of 0 is negative 4. So we're at the point 0, negative 4. 0, negative 4. That's when t is equal to 0. And in the last problem, we figured out what happens when t is equal to 3. We figured out that x is at 21. X is at, I'll just say that's 21 right over there. X of 3 is 21, and y of 3 was like negative 3 point something. So it puts us right over here. So this is 21, and we figured this out in the last problem. I think it was negative 3.226. And so this is what happens when t is equal to 3. And between these points, we don't, who knows what the path is. We could plot it if we wanted, but it might look something like this. So who knows what it does. And we go like that. And so in part D right here, they're asking us what is the total distance traveled, or another way to think about it is what is the length of this path. And there is a formula for arc length, and if you know it, you could just apply it, and it's not a bad thing to know going into the AP exam, especially if you're under time pressure, but I always forget what it is. I'm almost 35 now, so I always like to re-derive it, and there's always something a little bit satisfying about that too, because we remind ourselves why the formula works. So we could take a little bit of we could try to think about, well, how do we figure out a little bit of that arc length? So actually, let me do a little other part. I like this part more. So let's say, how do you figure out a little bit of that arc length right over there? So a little bit of, let's say you have that little bit of an arc length that I'm going to zoom in onto that. Well, you have a little bit of a small change in x. So let me draw it. You have a small change in x over that arc length, which I've blown up. So call that dx. And you have a small change in y as well. You have a small change in y, dy. And we know from the Pythagorean theorem, I mean, this is, if we get small enough, you can approximate this as just a hypotenuse. This is the base, this is the height, and this is the hypotenuse. And so this is going to be, especially if you get these small enough, a line is going to be you could really approximate this arc by the hypotenuse, but right over here, I'll draw it right over there. We know what this is from the Pythagorean theorem. This is going to be the square root of dx squared plus dy squared, straight up from the Pythagorean theorem. Now, how do we write these as functions of t? Well, we know that dx dt is equal to x prime of t, or if we treat differentials kind of like numbers, and you can most of the time, this is not very rigorous, but we know that dx is equal to x prime of t dt. And we know that dy of t, or dy dt, we know this is the same thing as the derivative of y with respect to t, y prime of t, multiply both sides times dt, you get dy is equal to y prime of t dt. And all I'm doing here is I'm essentially reproving or re-deriving the arc length formula. So we know that this right over here is just a small little arc length. So we could call that dl or dA for small arc length. Actually, we don't have to worry about what we have to call that right now. But this expression for that little very small arc length right over there, if I rewrite it in terms of what I have in terms of this and this, what I have on the right hand side, and I want to do that so I can get everything in terms of t, I get it is equal to the square root of dx squared. Well, dx squared is the same thing as, I'll do it in that magenta colored, that is x prime of t dt squared, and then you have plus dy squared, and dy squared is just this stuff, y prime of t dt squared. I never make my radicals big enough. There you go. And so this little arc length is this right over here, and then you can actually factor out a dt squared. So this is going to be equal to dt squared times x prime of t squared plus, I'll do this in green, plus y prime of t squared. And then, of course, you can factor out the dt out of the radical sign now. The square root of dt squared is just dt. So all of this simplifies to, I'll write it in yellow, this simplifies to, this part right over here is x prime of t squared, and this part over here is y prime of t squared, and then we factor out the dt. We factor out the dt. Now this is all just a way to derive what this little small d arc, or this little small arc length is. But we don't want to find just a small arc length. We want to sum over all of them. So what we want to do is integrate the dt's, take the infinite sum of these infinitely small pieces right over here, these infinitely small arc lengths, from t is equal to 0 to t is equal to 3. And so now we just do it. And so they tell us what x prime of t is and what y prime of t is. Let me just rewrite the expression. This is going to be equal to the integral from 0 to 3 of the square root, I'll make my square root nice and big here, of x prime of t squared. The problem, they give us what x prime of t is. It's 4t plus 1. 4t plus 1. So it's 4t plus 1 squared plus y prime of t squared plus y prime of t squared. The derivative of y with respect to t is sine of t squared. So sine of t squared, and we need to square that as well, squared, and then dt. And this is not a simple thing to find the antiderivative of, but lucky for us, we are allowed to use our calculators in this part of the AP exam. And so all you have to do at this point, you've already done really the hard work, is use this definite integral function. It's in our catalog right over here, and you can go straight to the f's. Straight to the f's, so I'm going to go page down. So there we go, definite integral. We need to find the definite integral. We have to punch this into our calculator of the square root of, and I'll write it as x's just because the x button is much easier to get to than trying to put a variable t in there. So the square root of 4x plus 1 squared plus sine of x squared. I'm just, instead of writing a t, I'm writing an x here just to clarify what I'm doing. Sine of x squared, and then we want to square that squared. Let's see, so that closes that parentheses, and then I need to close the radical parentheses right over there. I want to say that my variable of integration is x. I could have put t's here and said my variable of integration is t. There's no difference there. And then I'm going between 0 and 3. And so let's see, let's let the calculator do all the work here. And we get, it's taking a little time, we get 21.091. So this is equal to 21.091. And that's the entire arc length. That's the distance that this particle traveled.